Welcome to This Explainer. Today, we're unpacking a literally mind-bending breakthrough that finally bridges the gap between abstract quantum physics and everyday medicine. We're looking at a first-of-its-kind study that takes something previously confined to highly controlled physics labs and brings it right into a standard hospital room. Let's start off with a pretty provocative thought. What if the invisible, seemingly sci-fi mechanics of the quantum realm could actually be used right now to look inside the human body and spot a tumor? We often think of quantum entanglement as Einstein's spooky action at a distance, something that has absolutely nothing to do with our biology. But this new research proves that the quantum architecture of our cells can in fact be mapped and measured in vivo. We've got an amazing roadmap for today. We'll explore this quantum medical leap, see how it moves beyond standard PET scans, decode the entangled photons, look at the plastic JPET solution, review those incredible first-in-human results, and finish up with the future of diagnostics. Let's jump right into part 1, a quantum medical leap. Grounding this in physical reality, we're talking about the actual 60-kilogram modular JPET scanner used in the clinical study. This isn't theoretical math on a chalkboard. It's a real machine sitting in a hospital setting. Its split half-cylinder configuration means it's highly portable. You can literally roll it right up to a patient on a standard diagnostic bed. And crucially, it's built entirely from plastic scintillators, which is a massive departure from traditional, heavy medical imaging equipment. Moving to part 2, going beyond standard PET scans. Think about the fundamental difference here. Standard PET scanners give us a basic heat map of metabolic activity. They track where and when photons interact, but they essentially throw away the angle of the scattered photons. Just toss it out. The JPET scanner, though, uses that scattering angle like a secret code. By tracking it, the scanner generates a highly unique biochemical fingerprint based on quantum entanglement, entirely bypassing the limits of those conventional crystal-based detectors. Section 3 is where it gets really interesting: decoding quantum entangled photons. To break that secret code, researchers use a totally new metric called CQE, or the degree of quantum entanglement. This is a brand new molecular biomarker. It actually measures the entanglement between photons that are created when matter meets antimatter inside the patient's body. And what makes this so groundbreaking is that this value isn't static. It fluctuates dynamically based on the specific molecular structure and oxygen levels of the surrounding tissue. Let's break down how this works mechanically. When these photons are born, they're naturally quantum entangled. Standard scanners lose that delicate quantum information almost immediately. But the JPET, by using those plastic scintillators we mentioned earlier, interacts with the photons differently through the Compton effect. It can simultaneously record the position, the time, and crucially, the relative angle between the scattering planes. By capturing that exact angle, researchers can study the entanglement state without destroying the data. So let's look at part 4, putting this into practice with the plastic JPET solution. This timeline really grounds the data in a human story. We're looking at a 48-year-old guy who had previously had surgery for a pancreatic neuroendocrine tumor. At 0 minutes, he gets a standard radiopharmaceutical injection. After 55 minutes, he goes through his routine scan to check his postoperative status. But then, at the 90-minute mark, he's moved to the JPET scanner for a 20-minute scan of his abdominal cavity. In those 20 minutes, he became the very first person in history to have his quantum entanglement measured in vivo. Which brings us to part 5, those awe-inspiring first-in-human results. It is incredible to compare a standard metabolic heat map against the precise spatial distribution of actual annihilation points. The team isolated the liver and spleen for their quantum analysis, framing 3-dimensional regions of interest around them. They took the raw hit data right from the scanner, reconstructed the exact points of entanglement, and then overlaid that data directly onto the patient's CT scan. And here is the monumental result. The data revealed a CQE entanglement score of 0.79 for the liver and a closely related 0.76 for the spleen. To put that into perspective for you, a score of 1.0 would mean maximally entangled photons, while a score of 0.5 would mean completely independent separable photons. So these numbers, 0.79 and 0.76, are non-maximal, but they are definitively higher than non-entangled photons. They are hard proof that entanglement survives within human tissue and can be quantitatively measured. Now, capturing those specific numbers meant the team had to meticulously filter out a massive amount of background noise. The scanner sees random scatterings and overlapping signals everywhere, but by measuring the exact energy deposited in the plastic strips, what they call time over threshold data, the researchers essentially built a quantum noise-canceling filter. They suppress the false hits and manage to isolate only the true, verifiable, entangled photon pairs. Finally, let's zoom out to part 6, the future of diagnostics. Why does all this matter? Because that entanglement score isn't just a fun physics fact. It is deeply tied to our biology. The entanglement actually drops when a positron collides with a random electron in your tissue, a process known as a pick-off annihilation. Because different tissues have completely different molecular architectures and porosity, the rate of these pick-off collisions changes. As a result, the final entanglement score acts like a highly sensitive molecular probe, directly reflecting the biochemical composition of a specific organ or even a tumor. As the authors perfectly state, this has the potential to fundamentally transcend how we diagnose disease. We're no longer just looking at where a radiopharmaceutical gathers in a blurry heat map. We are actively reading the quantum state of the tissue itself. We are turning quantum entanglement into a brand new, powerful medical biomarker that could one day distinguish between healthy tissue and various types of pathology purely based on a quantum signature. And that brings us to a pretty profound realization. If a portable plastic scanner can now read the quantum fingerprints of our internal organs in real time, we have to ask, what other diagnostic secrets are waiting to be uncovered inside our own quantum architecture? As this technology scales to total body scanners, we aren't just improving medicine, we are literally entering the era of quantum biology. Thanks for exploring this with me today, and I'll see you in the next one.